Okay, here we go. So we're going to talk about some inverse functions. From Precalc, tell me what you know about inverse functions.
They undo a function that goes forward.
Give me an example.
Inverse cosine. Right? We'll undo cosine.
We'll undo cosine.
Yeah, so if you have cosine x, and you take the inverse cosine of cosine x, you get x.
So if I have a function like x squared, what's the inverse of x squared?
One over x.
Anybody else?
X to the 1/2.
No, that's a reciprocal.
X is like square root x.
Square root of x, right? So they're the things that undo the function. So if my function is adding 2, I would undo it by subtracting 2. What we're going to be doing today is not necessarily working with inverse, well, we will be working with inverse functions, but our primary goal today is learning how to take the derivative of an inverse function. Okay, and I'll give you a couple different approaches to that. So we'll do quite a bit of pre-calc review on inverse functions, like how you get them, what do they mean. I've got some new terminology for you today. We'll determine whether or not a function has an inverse function. Not every function has an inverse function. And then, of course, today we're going to find the derivative, and then lastly, you should be nice to people. Okay, great. So, some pre-calc stuff. Notice the notation here. F to the negative 1 power is not a reciprocal, it's an inverse function. It's the function that undoes the other function. These two little sentences are really important. If a function has an inverse, and if you create a composite function of the function and its inverse, what you end up with is x. Which, in the examples that we looked at, if I take the square root of x squared, I end up with x. If I take the square root of x, no, I said that one. If I take x squared and take the square root of it, I end up with x. When you're verifying that two functions are inverses, you have to do both of these. Put the function into the inverse, put the inverse into the function, and show that they both end up getting back to x. The other thing that's really helpful, which we'll get to later, is the fact that the domain of the function is the range of the inverse. And the range of the function is the domain of the inverse. So the x's for one is the y for the other. And you've seen all this before, right? Yeah. Good. Okay. So here's our two functions. What? What do you need? Are you writing that whole paragraph down?
No.
Okay, good.
It does say
It says what?
important.
I'm not denying that.
Oh, you put it
I put it there, correct. Okay. Are we good?
Almost out. Yeah.
So I think F and G might be inverses of each other. So I need to verify that. And as I said, I have to verify it using both techniques. So I'm going to do F of G of X, and I'm also going to do G of F of X. Let's start with this. I'm going to take this, G of X, and put it into F of X. So I get 2 times the quantity, the cubic root of x plus 1 over 2 cubed minus 1. What happens when you cube a cubic root? It cancels. So 2 times x plus 1 over 2 minus 1. Oh, look, the 2's cancel. X plus 1 minus 1 gives me x. Halfway done. Odds are they're probably inverses, but we got to check the other way. Now I need to take f of x and put it into the function. So I'm taking the cubic root of 2x cubed minus 1, that's x, plus 1 over 2, which is the cubic root. Well, the 1's go away, the 2's cancel, the cubic root of x cubed is in fact x. And so we know that those are inverses of each other.
Do you have to do both methods?
Have to do both ways.
Every time?
Yep. There are certain bizarre instances where it works one way, but not the other way. So you check them both and you're good to go. Got the sniffles?
I'm sick.
I know. Thanks for bringing it with you.
You're welcome.
Rate it on your quiz tomorrow that you're sick.
Did you not see the last point? Be nice to people. I'm a person. I have feelings. We did that already? Okay, so we got that, so they're inverse functions. All right, now this is an important point about inverses that I don't know if you learned last year. If you graph a function and its inverse, they are reflections of each other over the line y equals x. So the red one is the line, the one that's labeled, y equals x is the line. The black graph is the original function f of x. The gray graph is g of x. And you see that that is a reflection of each other. That's going to be crucial to what we're going to do later. So you need to remember that. I think I have that written down too, so you can write it. Okay. The red is also important. If I pick a point on the function, the point AB for instance, its corresponding point on the inverse would be the reverse of that, BA. AB becomes BA. If 2, 3 is on the function, then 3, 2 is on the inverse. If 10, 5 is on the function, 5, 10 is on the inverse. That's also an important point. In my humble opinion, I'm going to show you a graphical approach. I think that's the easiest method to approach these derivatives. There's also an algebraic approach and there's a formula approach. I'm a big fan of the graphical approach. So you're going to need to know this kind of stuff in order to use that approach. I just said approach about 8 times in the last sentence. Okay, we good? Yeah. All right. Here we go. So, horizontal line test, remember that? What's a vertical line test? Whether it's a function. Okay, so think about it this way. If I have a vertical line and I reflect it over the line y equals x, it becomes a horizontal line. So the horizontal line test is the reflection of the vertical line test. The vertical line test tests whether or not something is a function. The horizontal line test tests whether or not it's whether or not the inverse exists, or the inverse is a function, I should say. It works the same. If it hits the graph in more than one spot, its inverse is not a function. The best example of this is the function x squared. You reflect x squared over the line y equals x. Let's draw a picture here for the visual learners. Take the function x squared. Is that a function?
Yes.
Yes, it passes the vertical line test. I take its inverse, which would mean I would reflect it over the line y equals x, and I would end up with something that looks like this. Is that a function?
No.
No, because it doesn't pass the vertical line test. So we can skip this step and just go right to the horizontal line test and say, oh, you know what? I can draw a horizontal line through that graph. It hits here and here. It hits in more than one spot, so therefore the inverse is not a function. And hopefully you did that in pre-calc, yes?
Yes.
Yes? Okay,
Yes.
good. There's the fancy schmancy stuff. The only reason I put this up there is because of this little phrase. Strictly monotonic. Sounds cool. Anybody have any idea what strictly monotonic means?
I mean, it only has one x, y combination.
No, that would be 1-to-1. Good guess though.
Only works one way.
I'm sorry?
It only works one way. You can't like do it on another graph.
Close. For our definition, not for our definition, the definition of strictly monotonic as it applies to this is going to be simply, it's strictly monotonic if it's always increasing or always decreasing.
So if it passes the horizontal and through, that's right.
Yeah. So for instance, x squared would not be strictly monotonic because it's decreasing and then increasing. We can use this concept of strictly monotonic to look at the inverse of the function and use that to determine whether the inverse of a function is also a function. Okay, so the stuff in the box is not really important. It just gives me an introduction for you for that term strictly monotonic. Okay. Two simple questions. Which of those, if either, have inverses? And we're going to take a calculus approach to this. So one way that you could graph it and see if it passes the horizontal line test. You could figure out what the inverse is. We'll do that later. But we're going to use calculus to see whether or not these things have inverse functions by looking at the derivative. Okay, so what's the derivative of part A? I think I have that here. Here we go. There's the graph. And so looking at the graph, you can tell that has an inverse function because it passes the horizontal line test. No matter where I draw a horizontal line there, it's only going to hit in one spot. From a calculus standpoint, we can take the derivative, and what can you tell me about that derivative?
So it's always
I probably already have it written there. Yeah, there it is. It's positive for all x values. Which means, if it's always positive, well, you tell me. If the derivative is always positive, what do you know about the function?
Increasing.
It's always increasing, therefore strictly monotonic, and therefore it has an inverse function. Okay? There's the first example.
So do you have to take the derivative every time you want to see if it is like?
It's one possible way to do it. If I give you the function and the picture, I would definitely go to the picture every time. See if it passes the
But if
horizontal
you
line
don't
test.
have that, do you recommend like graphing it on your calculator? Or
If you have your calculator, yes. But what if this shows up on a non-calculator question and they don't give you the graph? But in other words, if I gave you just this, whoops, do you know what part B looks like, for instance? Right, how does that, x cubed, no problem, you know what that looks like, but how does that minus x plus 1 affect the graph? So without having a calculator, what I would do is take the derivative. So before I click on the slide, let's do B together then.
Can you explain that one more time?
Yeah, I'm going to do it right now. So I'll explain it by doing an example. If I find f prime of, oh, that's an ugly color. Can you guys even see that color?
Yeah, I can't see it.
F prime of x is 3x squared minus 1. What can you tell me about that? Is it strictly monotonic?
no.
No, because it can be positive or negative, which means it's going to have increasing and decreasing portions, as opposed to this, which was 3x squared plus 1, always positive, therefore strictly monotonic. So since f prime in part B is not strictly monotonic, then it doesn't have an inverse function. Does that help, Tiana?
Yeah.
Okay. So there's A, we did that one already. Here's B. So graphically speaking, like I said, if you got the picture, doesn't pass the horizontal line test, done. If you don't have that, then you got to go and find the, where are we doing it? There we go. Find the derivative and show that that derivative is not always positive nor always negative, so therefore it's not strictly monotonic and has no inverse. Okay, so there's two approaches to solve the same problem. And again, in a perfect world, like Ashton asked, I would always go to the graph first. See if the graph passes the the horizontal line test. And if it doesn't, you got to come up with something else, and in this case, you can use the calculus. Okay, how are we doing so far? Not bad? I'll take that as a not bad. Okay. Now, how to find an inverse function. Before I click on this, tell me, how do you find an inverse function? If I give you f of x and I want to know what the inverse function is, how do you go about finding it from Precalc? Lucas.
Replace x with y, and if you exchange x and y and try to solve for y.
Perfect. Well, confirm now that we're talking about calculus, you confirm that it has an inverse, Because in pre-calc, you probably didn't do that, you just said, go find the inverse of that function. Confirm that it is using one of the techniques we talked about already, horizontal line test, strictly monotonic. And as he said, exchange x and y, solve for y.
So the inverse is not a function, it's not an inverse.
If the inverse is not a function, then we don't really consider that an inverse. That thing you end up with when you solve for y is your inverse function. We talked about that already. The domain and the ranges are opposite on the inverse and the function. Oops, sorry. Anybody know what time the bell rings? 40? Oh, we're not gonna get this done. So we'll do the best we can. Okay, we good? The most important one are 1 through 3. 4 is just a notation thing. 5 we already knew. Domain and range switch. So let's go through an example first, and then we'll see how we're doing for time. All right, find the inverse function of that. First of all, does it pass the horizontal line test? Do you have any idea what that looks like? Well, get out your calculators, take a look. Graph that quickly, see if it passes the horizontal line test. I'm guessing it looks like a stereotypical square root function, which is the whole, you know, this thing.
Oh,
I'm guessing it's going to look something like that. Yes, sir.
I need to.
I'm not a trained psychiatrist. Oh, wow, that's not good. That's a stat thing. I'm out.
Wait, do you know how to turn it back?
I'm out. Nope. Nope.
No.
I don't go there.
What is it?
This is such a bet.
I see it?
Can somebody confirm, does it look something like this?
Yes.
Okay, good. Is that sufficient, or do we need to do the strictly monotonic thing? Are you happy with this?
Yeah.
Okay, good. Well, suppose I wanted to check that it's strictly monotonic, what would I do? Take the derivative, look at the derivative, see if the derivative is always positive or always negative, and then we'd be good to go. The derivative would contain a square root, so it's going to imply that it's probably always positive or always negative, so we're good to go. Okay, so this is y, so we're going to change that into x, and then change the x into a y, and solve. How do I get rid of the square root? Square both sides. Add 3. Whoops. Easy. X squared plus 3 equals 2y, so y is equal to x squared plus 3, all divided by 2, which, just to keep our notation correct, that is the inverse of f, which is x squared plus 3 over 2. Okay, easy. However, when we start doing derivatives, this is the last thing we want to do. Okay? You know how to find an inverse. We can find the inverse, but it's not always the most practical way to approach calculus problems involving the derivative of inverses. It's one of the 3 techniques I'll show you, but number 3 on my list of priorities. Can I erase this? Oh, wait, I did that already. Okay, great, yeah. Come on, let's go. Here we go. Yep, there's the graph. Okay, yep. Yeah, okay. Did that, yep. I don't know why I did this. I had it all. Yeah, okay, verify it. Yeah, it works, great. There's both methods. Put the inverse into the function, put the function into the inverse. They both equal x. We're great. Okay. Now the derivative. Okay, so